Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leader series, Mass Timber Design for Structural Engineers. My name is Megan Purdy and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past, present and emerging. Before we get started, I would like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, XLAM. For over a decade, XLAM have been manufacturing and supplying mass timber to projects across Australia and New Zealand. They lead the market in the manufacture, supply and design of CLT and GLT structures and in providing extensive specialist technical advice, documentation, certifications and support to their clients and project partners. Now today, we will hear from two speakers followed by our live audience Q&A. So I encourage you all to please send your questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Fiona Zhang, Senior Structural Engineer from XLAM. Fiona has 11 years experience in structural engineering with diverse engineering skill design of reinforced concrete, post-tension concrete, steel, composite structure, and 10 months experience in mass timber design, including cross-laminated timber, with hybrid steel and timber structures. She has worked to deliver projects in various fields, including the Star Casino redevelopment and sovereign mid-rise to high-rise commercial and residential buildings, schools, hospitals to high-end houses. Fiona has been passionate about sustainable design and is always looking for ways to optimise structural efficiency and minimise environmental impact. Please join me in welcoming Fiona Zhang.
Hello everyone, my name is Fiona from XLAM. I have 13 years experience in structural engineering, worked with concrete, PP and steel. I've joined XLAM in April last year. Today I would like to share my learning experience with mass timber. First, a brief rundown of who we are. XLAM Australia, as part of High-End Timber Group, has 10 years history in manufacturing CLT, start from New Zealand and moved to Wodonga, Victoria from March 2018. High-End Timber owns and operates two sawmill and GLT manufacturing plant, two sawmill, one in Tabaramba and one in Maroubra. The Maroubra has the GLT manufacturing plant as well. 100% XLAM feedstock is supplied from Tabaramba sawmill with untreated and treated. So today we're going to cover the standard and guideline for mass timber design, the material behavior of timber versus steel and concrete, the failure mode of CLT and glulam, and the moisture content of mass timber is the key one. The key consideration in structure design and analysis, and finally, the connection. First, the standard and guideline for mass timber design. For what's mass timber? So the NCC defined mass timber as an element not less than 35 mm thick, as measured in each direction, formed from solid and laminated timber and includes glulam timber. Is layered of dimensional lumber bonded together with adhesive, normally used for beams, columns, and timber trusses. And LVL, bonded thin wood veneer with adhesive under heat and pressure. We normally use for beam, headers, and rafters. And thirdly, or CLT, which is made by stacking layers of wood panels in alternating direction and bonding together with adhesive, mainly used as walls, floors, roofs, and stairs. Today, we'll mainly focus on our product, glulam and CLT. For glulam, you can see there's all the size, the thickness from 65 mm thick up to 130 mm thick, but the size can go up to 260 by 1.2 meter high by block glue members. You can, from the image, you can see how big it can be, and it can be used for long span truss for warehouse. For example, the span can span from like 35 meters up to like 40 meters. For 35 meters span, and the depth need to be 3 meters deep at the pitch. This as an example. This is a CLT standard panel size. It has a split 3 layers up to 7 layers. We have our XLAM guidance on the span table with without FRL and with FRL. The common use is 3 layers 120. It can stay on the steel beam, which span like 4.1 meters, and it's all can do the continuous span with 5 layers to 20 mil thick. It can span up nearly like 6 meters with to continuous span. So the standard guidance we normally use is the Australian standard 1720 and Eurocode 5, which just covers Australian standard doesn't have. Tom in the next session will discuss more about that. And other materials from O Solution, and there's one book called Protocols and FP Innovation, the Canadian version of the CLT handbook, are very useful. Also, we have our technical note and guidance available. The material behavior of timber versus steel and concrete. Firstly, come with bit knowledge in timber material regards to the grain direction. There are more inference in radial direction than longitudinal direction. You can see from here. For the shrinkage and swell, it has a lot more in the radial direction than the longitudinal direction. So normally it's about 0.1% to 0.3% along the radial, and the 2% to 10% transfers to this direction. So now from the table, you can see the characteristic value of the timber in different grain direction. With the tension capacity along the grain is 7.7 for the tensile strength versus only 0.5% only 0.5 MPa and along the perpendicular grain. Also for the bearing, the compressive strength along the grain is 3 times than the perpendicular grain. There'll be a lot more inference in the radial direction than longitudinal direction. Apparently, we'll discuss the inference more in the moisture content and the connection section. Next is a characteristic value comparison of timber, steel, and concrete. From the table, you can see this chart is derived from this table. You can see the timber has very good tensile strength along the grain and good compressive strength along the grain. It has very good strength to the lightweight ratio, since the weight is only 20% of the concrete, and also its grain can store the carbon instead of releasing it. There's an interesting example, compare the structural steel and timber. So from this chart, you can see the behavior of the steel and the timber. For the similar room of 200 by 200, as a column, it has similar compression strength, and as a beam, it's not far away from the steel. It's just need to be like 1.2 times of the depth of the steel to acting at the same have the same performance. So timber is only 20% weight of the concrete. When we're looking to add additional levels onto an existing building, the lighter weight of CLT has a potential to reduce strengthening work significantly compared to the concrete or steel structure, or alternatively permit at great numbers of additional floors. The recent completed West Australia Square 2 project achieved 3 additional levels over what would have been possible with concrete floor. Also, for the poor ground condition, it has more benefit. So now for timber, it has a lot of benefit. It has high speed and safety. It requires smaller number of people on site workforce and no hard work such as welding. is lighter and easy to handle on site. Factory produced controlled environment can control the quality of the production, and it's quieter, and it's very good for the neighborhood and will have less impact to the existing projects right next to it. And there's a time lapse. It's only need 28 days to finish the assembly building on site. So the failure analysis on timber structure in Germany carried out by Blatters Fries gives a good overview of the distribution of main types of failure classified according to the construction, use, and region. The most common type of failure is along the grain. It observed as appearance of crack along the grain direction. Now let's focus on the structural failure mode of glulam and the CLT. The structural failure mode of glulam, when it comes to bending, you can see the rupture failure along the bottom fibers. And when it comes to tension failure, when it has a notch, and you can see it's open up, has a tension failure or delamination, possibly. The structural mode of the glulam for under compression, that's a crushing fiber. So for CLT, because it's a low strength along the perpendicular grain, so it's need to pay attention to the crushing failure. And with the shear failure, when it's come to the opening, just be careful. It's have high chance to have the shear failure near the opening, but we can do the strengthening by using additional screws or steel plate. This is the structural failure mode for CLT panel in bending when it's out of plan bending direction. You can see the tension failure started at the finger joint here, and also it's a rolling shear failure in the middle laminated layer. I'm gonna talk about more rolling shear after. So this is a structural failure mode of CLT panel in bending when it's in the in-plane loading direction. That's the bottom of the CLT panel. You can see it's open up. The failure starts finger joint at tension zone, and also is from the soffit of the CLT panel finger joint failure extend into shear failure and opaque granite to another lamination. This is a structural failure mode for compression parallel to the grain of the CLT. You can see the top and bottom, there's a shear failure, and this is a splitting failure between the lamella, and this is a crushing failure. And this is a structural failure mode perpendicular to the grain. There's a crushing, I just probably talked about. For the crushing, just be careful when we have the post and plate option. I need to pay attention to the crushing area. And this is a rolling shear, may happen with the same system, and this is a column penetration, but very less chance to happen. Now come to the rolling shear. Before, when I work with concrete and steel, I never know what rolling shear is, because the layer of the CLT, the mid layer in the mid layer of the perpendicular grain, just need to be careful. They have like a lower strength. When it start have the deflection, and it will start rolling. So normally the rolling shear is governing the design over the longitudinal bolt failure. Now let's focus on the moisture content of mass timber. What's moisture content? The moisture content is just a mass of moisture present in the wood divided by the mass of the wood without the moisture. The moisture change can lead to dimensional change of wood component. Shrinkage will occur when moisture change is reduced, while the wood will swell during the increase of the moisture change. With this chart, you can see that when we provide the manufacturing product, normally it will be controlled within 9% to 15%. When is more than 18%, it will start to have a risk of growing mold. But when it comes to 28% to 30%, it may have the more seriously risk of fungal or decay. The moisture movement and tolerance. As previously mentioned in the wood, so glulam is a little bit better. So it has a 0.02% of length change per 1% moisture content change when it's parallel to the ground, while along the radial direction, we'll have like 0.24% every 1% of moisture change. And the CLT has a little bit less impact due to the alternative direction of layered panel. The cumulative tolerance is very important when it comes to the very long building, and mid to high rise building need to be considered when they design the behavior of the building and also the connection design. Durability. XLAM CLT is manufactured from radiated pine, while the GLT manufactured from southern pine has low natural durability class 4 and the long-term suitable for class 1 and 2 use only. According to the AS 1684, it has 50 years service time when it's well maintained. It's need to follow the XLAM storage and handling requirement. The treatment can apply to the wet area, such as like bathroom, kitchen, and laundries, where it's close to the ground with high humidity or difficult to inspect. Extended period when moisture content more than 80% can lead to the issue I just previously mentioned. In all cases, surface must be less than 18% moisture content before any finishes applied. Consider compatibility with temporary treatment. Panels end need to be sealed. Construction planning and drying an important consideration. Waterproofing and prevent from leaking are very important. The long-term moisture monitor and control plan for moisture content less than 15% is important. Some of the large building in the Europe or Canada, they are using some monitor system embedded in the CLT panel to do the long-term monitor. The design and detailing need to be considered over temporary and permanent stages, include movement and cumulative tolerance due to the moisture change for large buildings. The key consideration in structural design and analysis. When you come to the first, when it's considered a timber building, how can we benefit from the timber building? CLT span less than 6 meters will be very compactive compared to the concrete floor to floor. We'll try to avoid the load transfer, make a simple load pass, and design for one-way continuous span system where practical to reduce the element. It can reduce the deflection and the vibration and make it more robust. So there's some example of the system, such as CLT walls and slab as a honeycomb, and the post and plate, and this is purely just post and the beam, like glulam. Now this is some knowledge about how to calculate for timber. The glulam can be calculated the strength in bending, shear, and the compression from AS 1720. Well, when it's come to CLT, as a composite section wasn't covered by Austrian standard, but we can use the gamma method and the shear knowledge, consider the shear deformation to calculate the strength and the deflection. We have our technical note for the sample of calculation, and also we have provide the EI effective value and EI apparent value for the designer to use to design the CLT panel. Also, we have our span table for the CLT and also the span table when it's come to fire to satisfy the fire rating. When it comes to the serviceability of timber, be careful. The timber has a creep factor, not like concrete. This one is a lot more, need to be more seriously. So that one can be up to the J2 factor can up to 2, which is we double the deflection result when it's come to permanent case only. The J2 factor is very important. It can double the deflection when it's under the permanent load. So the program we use, the RVM is from Dubo, is we use the most. Is very good with composite structure. You can put the layers, have all the characteristic value can put in, and also we have the stiffness and matrix value, which can be used for other program. So modeling tips, the hinge joint is very important for CLT design, and it wasn't covered by Australian standard, but you can find from Eurocode 5. We can modeling the timber to timber fixing by introduce the hinge in the model, and it can influence the deformation of the building, and also provide the penalize of the floor plate. Here's the bottom is an example with modeling with a joint and without the joint. You can see the difference with the frequency. Next is a FRL and combustibility. Timber can char, and people will question, oh, when it comes to timber, oh, how about fire? But timber is combustible, but it can char. You can see this chart. This is the chart for 3 layers for CLT. And when it's charred, it takes time, but it will preheat the next layer. So you can see a little bit acceleration here, but then it will slow down when this come to the end, but accelerate again. We can design the CLT panel, consider how much time will take for the charring, or can use a plasterboard or non-combustible material cover the timber, or use a self-extinguishment plan by the fire engineer. Now we need to think in advance. The maximizing the benefit of DFMA, the design for manufacturing and assembly, to take the benefit of the CLT. Avoid clashing with services need to be considered early, and don't forget the potential impact from the moisture content change, which can affect hugely on the connection and the performance of the building. And need to think about connection design in advance when we determine the member size, which will be covered more in the next section. Connection. Now is a key consideration for connection design. When it comes to connection, we need to try to reduce connection type and design for simplicity in connection to maximum the benefit of the FMA. Use the right standard for selected product. Ensure the minimum spacing and edge distance is achieved. Attention to the force direction regarding to the ground direction, which we have covered hugely in the previous talk. The sufficient residual section need to satisfy the design, such as this fork detail. That's why personally I have mentioned we need to determine this. When we determine the size, we need to think about the connection. If it's still working for the CNC machine, or if it still have enough residual section for the strength. We need to minimize the potential for the tapered water, for the trapped water, and maximum the water shedding. We will try to maximize the inspectability, just prevent from any mold or fungal happen. The tolerance for installation and moisture change need to be considered and included in the design. We need to reduce a permanent action on the fastener where possible. Try to use a bearing connection. The ductile connection for wear CLT acting as shear wall and diaphragm is important when we come to resist the seismic force. Timber will normally use grade 4.6 volt compared to the grade 8.8 volt when we use for steel and concrete. We need to consider the CNC machine capability. The glue lamp connection can vary greatly and contribute from 10% to 4% of the material cost overall. Now this is another example of the glue lamp bottom base connection. We're trying to prevent from the issue with water trapping. Let's come to see the board connection failure mode. The embedment failure is covered by Australian Standard 1720.1. While the Eurocode 5 covers more detail, you can see there's a splitting and rope shear and block shear net tension. Especially the block shear, you probably wouldn't consider for concrete and steel design. There's some example of the CLT panel connection. On the middle, in the middle, that's the lap joint, half lap joint. While on the right hand side, that's a spine joint. We have our technical note to show some example of the connection, and also our team can provide the design services for the connections. Sometimes we would like to use a proprietary product because it's just off the shelf available, and the prefabricated products are usually lower cost than the fabricated steelwork. And there's another example when it's come to the shear wall. This is connection, the floor to wall, and the connection, the timber wall to the concrete. The tension is not taking, we'll consider this type of the connections taking the tension, while this bracket is only take the shear. So CLT has some limit, but we can overcome the limit by working with concrete and steel. And there's an option for timber composite. We have the band beam and rep deck, which is using glue lamp and the CLT. And Tom is gonna cover more about the band beam system. And timber to concrete composite, which is a TCC. You can see the bottom two. There's a two example, like one has a pickle delta beam, have the higher strength to achieve the long span, and the CLT can just sit on each side. And also another type for the TCC can help with the vibration. And also we can, there's some like a hybrid structure. So CLT can be used as a floor diaphragm within the hybrid system with a brace steel frame or with a concrete core. In these buildings, the CLT is used with established construction approach, and the best of both worlds can be targeted. The system can offer higher span and assist overcoming the limits on building height and the span, and the vibration requirement. So there's another example, the famous project at Atlassian. So there's another thinking for people, like we can insert there are three levels of CLT insert in the building. So it can think about overcome the height of the building. So don't forget your skill in concrete and steel, we can cooperate. Thanks for attention.
Thank you, Fiona, for your input today. I'd now like to welcome our second speaker, Tom Watts, Principal Structural Engineer from XLAM. Tom has 15 years experience in the construction industry in the design of concrete, steel, engineered timber and other structures. He has experience across a range of new and refurbishment of existing buildings in local and overseas projects in engineering consultancy and timber design manufacturing businesses. His experience on mass timber projects began in 2015, and he has worked on a number of significant mass timber projects in Australia. He has coordinated with fire engineers, government agencies, and building certifiers for fire engineering assessments, testing, and performance-based strategies for achieving compliance in exposed timber structures. At XLAM, Tom leads a small in-house design team to provide services to the market, collaborating with architects, engineers, suppliers, and builders to achieve high-quality mass timber buildings that are easy to construct. The team also has a focus on developing new applications for projects using CLT and other mass timber products. Please join me in welcoming Tom Watts.
Thank you, Megan, and thank you for the introduction. Hello, everyone, and thank you for having me here today. It's a privilege to speak to everyone today, and thank you for your time, and thank you also to Engineers Australia for hosting this event today. Just by way of a quick introduction, I joined the XLAM team in 2020, and I'm based in Sydney, where I lead a small in-house team consisting of structural engineers and structural modelers. In this team, we support the increased use of CLT in the market through providing structural design services to our customers. We also support the sales and technical management teams within XLAM. So my experience back in mass timber started back in 2015, and since then I've enjoyed working on mass timber projects more or less daily since then. Initially I started working on mass timber when I was at Lendlease within the design make business before joining XLAM about 4 years ago. And so getting started in mass timber, I was particularly fortunate to get involved at a time where there was ample time to learn the new skills that were required on live projects with people who had brought these new skills in mass timber and expertise to Australia. And that has continued to this day through my role at XLAM, getting fortunate to work in carrying out this design work within a manufacturing firm environment, gets great insights to the end-to-end process of mass timber. So getting into the presentation. So in the first part of the presentation, Fiona highlighted some of the challenges faced by a designer new to mass timber, sort of coming over from a background in steel and concrete structures, and I can personally relate to that because I was in that position myself some years ago. And in this presentation, I'll build on some of these topics, and we'll focus on areas around the detailed design and compliance of mass timber in buildings in Australia. And the aim is to provide information that assists designers that are relatively new to mass timber projects, assisting to develop their designs and have confidence that the mass timber and CLT can be designed to give safe and compliant structures. So the main focus is going to be on structural engineering, as that's my main area of expertise, but with reference to some aspects of fire engineering in several parts of the presentation. So to start off today, we'll start off with a snapshot of our view of the current market of mass timber buildings, and then the presentation will look at the BCA and NCC 2022 structural compliance aspects. We'll look at some of the certifications that can assist that compliance pathway, and then we'll look at a little bit of fire compliance, some of the quality assurance aspects that can be considered, and I guess the main chunk of the presentation will be looking at what can be designed within the scope of AS 1720 Part 1, what aspects are beyond the scope of 1720 Part 1, and finish up with a little bit of information on residual cross-sections and how that can be considered amongst the 1720 and design and compliance pathways. So to start off with, I thought it would be worth giving a quick summary of some mass timber buildings, where the current market position is. And the market's come a long way since the first mass timber building in Australia, and that was Forte Living in Melbourne back in 2012. By 2024, XLAM have now completed approximately 1,000 projects in the market, and these buildings have been across most of the building classes. The offices, accommodation buildings, public buildings and houses, they continue to be a strong part of the market. We see developing interest in industrial buildings and modular buildings as well. And some of the photos on the screen there is just some of our recent projects, and you can see they're very varied and diverse projects. The top left is a little hotel down in Melbourne, good example of a small footprint, very tightly constrained site that was executed in CLT on top of a heritage building. The bottom left is Maryborough Fire Station. The top right is a commercial building with some nice glulam trusses, and the bottom right is probably more snow than you see on most projects in Australia, but that's a nice mass timber ski chalet. So we see these new developing markets, but then things like the vertical extensions, restricted site access, and speed of construction remain key drivers for our customers. So looking at the mid-rise project in a bit more detail, which is, I guess, a particular area of interest for XLAM in the scale of projects and where mass timber can start making a bit more of an impact on the traditional construction market. This was a study done by a group of architects looking at some projects that were completed between the year 2000 and the year 2021. And what they were trying to do was just draw out conclusions of what are the most common aspects and the key aspects of these projects. And I guess by what stands out as being really sort of common to a lot of these projects, and certainly what we see as being key to being efficient in the mass timber projects, is the orthogonality of these projects. By far and away, most of the projects are fairly rectangular, boxy buildings without too many steps in the floor plate. So this keeps really the uniformity of and simplicity of detailing key, which is an important part of making the projects economical, and just avoiding things like load transfers and complex structural systems that add to the cost of the system and can make the timber projects prohibitive in some cases. It's also worth you can see that the vast majority of projects were carried out using a combination of materials. Pure timber projects only made up 22% of the projects, so you can see there's still a strong component, a majority component of the concrete and steel aspects being brought into these projects. So when we're designing a structure of a mass timber building in Australia, we're operating under the requirements of the NCC. And like any other building, to demonstrate the performance requirements of the NCC are satisfied, the design can progress under either a performance solution or a deemed satisfied pathway. There are some parts of the design of a CLT building which can be covered under the deemed satisfied provisions, and this will be shown in the later slides. And typically these are the basic member checks which can be done to a large extent under AS 1720 Part 1. There are other items, however, that will basically trigger the need for a performance solution. And I guess most commonly these are the connection details for the variety of different connections that we're looking at with mass timber. Most of these will either need to be considered with design information coming from the Eurocode, European Timber Code, Eurocode EC5, or looking at the use of proprietary brackets, which will have capacity information covered under the European Technical Assessment pathways. It's also worth keeping in mind that if a fully DTS pathway is a consideration, it is possible to achieve that with more traditional bolted style connections in a glue lamp structure, for example. To determine the design capacity for materials of timber construction, the NCC references AS 1720 Part 1. Now, within 1720 Part 1, there's a number of different timber materials that can be used. These include solid timber, plywood, LVL, glue lam, or round timbers. And at this point of time, it's, I guess, key to note that there's no reference for CLT included within AS 1720 Part 1. However, there's the option to comply under the other timber products and grades, which is in heading H under clause 1.31. So in order to qualify as an alternative timber product or grade, certain criteria needs to be met. And quoting the code, just highlighted in that section below, the timber products or grades not listed in this standard shall have properties established either by testing or evaluation methods that are consistent with those described in AS NZS 4063 series. In addition, timber-based products, modification factors for durations of load effects for strength and stiffness shall be determined on the basis of testing. So an example of some of these properties are shown in the table in the bottom right, and these can be found in the XLAM published structural design guide. And these properties have been determined based on the principles of AS NZS 4063. And I guess just to point out one of the factors of the XLAM CLT product, there's different properties between the inner and outer lamellas. So there's the inner and outer portions of the CLT. So we use a lower grade product on the inside and a higher grade product on the outside. And it's also worth keeping in mind that one of the things which is a little bit unique about CLT, so when you've got it's essentially a product which is bending on its flat. So all those properties of the lamellas have been determined bending on their flat axis rather than on their tall axis, which you would have for, say, traditional timber stud. So it can be shown that CLT meets these requirements, and then it's possible to use CLT under the general approaches of AS 1720 Part 1, and this can be considered as part of a DTS pathway. However, it also needs to be kept in mind that not everything can be covered under this application, and this is what I'll outline on the following slides. And also, that's sort of in relation to the member elements, but it's also all the components need to be connected together. And as I mentioned, a lot of the connections are outside the scope of AS 1720 Part 1 and therefore under the performance solution pathway. So to support our customers to use CLT as an alternative timber product, as I mentioned, under those acceptable products under 1720, the XLAM panels have been, we've sought a certification by the EWPA, that's the Engineered Wood Products Association of Australia, and they have a product certification scheme that XLAM is now sort of qualified under. So what the certification entails, it basically certifies that the XLAM panels have been manufactured or can be manufactured to ISO 16696 timber structures. Full title is there on the screen there. I won't try and read through the whole thing. But basically, the EWPA certification process includes auditing XLAM's quality framework annually, reviewing the qualification testing and the subsequent verification testing, and then ongoing monitoring associated with that. And the EWPA product certification scheme is also accredited under JAS ANZ. So some of the key reference standard that form part of the ISO 16696 standard are referenced on the screen there. I guess the key one being EN 351. And if you're really inclined, it's got a lot of really fascinating information there about how the structure of CLT and how it's all brought together. So that sort of sets out the broad framework of what CLT should be from a product point of view. And then the Australian standards listed below that on the screen there are really how the component pieces of that CLT are graded, assessed, glued together to form the CLT product. So you sometimes hear people saying that there's no manufacturing standards for CLT, which is really not correct. There's a lot of extensive information that goes behind this. Most of the components are within existing well-established Australian standards and certified by this overall ISO framework for the manufacturing of CLT, which is the same manufacturing standards that we reference in European manufacturers and others. So for parts of the design not covered under 1720 Part 1, as I mentioned, the performance solution pathway will need to be followed. And under this pathway, basically you need to pull in all sorts of acceptable references, industry accepted methods to validate and have a rational basis for the design that's going to be covered under the performance solution pathway. So this can be, there's well-known guidelines such as FP Innovations, the CLT Handbook, ProHolt CLT Guide, and there's the European standards are also referred to quite a lot. A lot of wood solutions guides, XLAM technical literature, and various European technical assessment guidelines. So once you've decided what aspects of the design need to be covered under the performance solution pathway, the designer just basically compiles all those, prepares the performance solution brief, and submits that as part of the overall structural design of the project. So jumping over to fire compliance briefly. So unless the project is a standalone house or a Type C construction, many projects will require fire-resistant construction in one or more areas. So a detailed description of this is not the intent of this presentation. However, it's worth keeping in mind that there are aspects of the pathway of DTS and performance solution that needs to be considered in relation to fire. So in the NCC, there is a pathway for carrying out a fully DTS pathway for mass timber buildings under the NCC. However, in our experience, it's actually quite rare, and I haven't seen a project that has gone fully down that pathway. There's normally one or more aspects which triggers the need to go to performance solution. It's not generally an issue. I guess the main value people often see in going the DTS pathway is it sort of can be perceived to be a more straightforward pathway. So in terms of the process that structural designers may need to be involved in, generally a two-stage reporting process is adopted, and this comprises initially the fire engineering brief, and then this is followed by the fire engineering report. So this process involves the relevant stakeholders who, in addition to the design team, client and building certifier, it may include the fire brigade, local council, insurers or other parties. So the purpose of the fire engineering brief is really just to communicate to the stakeholders and approval authorities what the basis of the fire engineering strategy will be. So the fire engineering brief, it sets out what aspects are intended to be covered under the performance solution, and then sets out how this is intended to be addressed in the later fire engineering report. So the key things that are normally set out in this is the FRLs of the structure. We're looking at sort of group number and non-combustibility requirements of the building. So what areas of the building may require to be made non-combustible, typically the building facade, or if it's a class 2 apartment building, typically all the interior walls of the building. And what the supplier should be able to provide designers with is all the testing and assessments to AS 1530 Part 4 to show the compliance with the FRL requirements. We can provide all the group number and fire hazard properties, and any other applicable information that is requested within the fire engineering report. And often this can be things like fire collars, different types of connection details, how different junctions are protected. So that's stuff that your material supplier can be able to assist with in conjunction with the design team. So XLAM have certified fire and load capacity tables, and that allows the walls to be specified for a load capacity at a given FRL and height under the necessary FRL exposure period and the applied loads. So things that can need to be considered, I guess if you've got those tables, you need to be careful when you're going outside the scope of that testing. So it's just really a matter of just getting that information over early to your manufacturer so they can point out potentially when you may be going beyond the range of what's available. So it could be things like large penetrations, certain types of connection details. It could be very tall walls or very heavily loaded floors. And the guides that we have published are intended to help identify those areas. But if there's any questions, the earlier that you can reach out and get your supplier involved is usually a great assistance. So jumping back into the structural aspects of CLT, when looking at member design, one of the key concepts to be across in CLT is how the composite section is to be considered. So the small diagram on the right-hand side is one that I find quite a useful aid, and it shows sort of a stack of boards acting from sort of a stack of single beams at the bottom through to a fully composite section at the top. So glulam beams are a pretty good example of a fully composite section, whereas CLT, they've got the presence of the transverse boards. So that section of CLT is comparatively less stiff in a full composite section compared to glulam. But also keep in mind that it's still a fully it's a fully glued section, but the reduced stiffness comes from the reduced stiffness of the transverse layers. That's a fully adhesive connection. There's not slip in the connection. It's due to the material properties in that transverse direction. So there's a couple of methods that can be considered when you're looking at the composite section. I guess the main one is, also the main two are the gamma method and the shear method. Both are related, but the key point to keep in mind is that they have different applications within the design. So the effective stiffness is EIF, EIEFF is what comes out of the gamma method, and that's really applied in calculations when you're looking at strength of the material. It's an ultimate strength. So the shear analogy, it's quite similar, but it's an extension of the effective stiffness, where it takes into account the additional component of shear deformation in the deflections. So once you've determined the section properties, XLAM also published tabulated section properties for both those EI effective and EI apparent section properties. Then you can feed this into the shear, bending, and compression calculations as a basis for elements of checks on walls and floors. So this basically allows you to cover off the basic flexural behaviour of elements within the framework of AS 1720. But there are also elements to keep in mind when you're going beyond that. So this is what I'm going to be pointing out in the next couple of slides. So the example shown here, an example of where AS 1720 does apply. So it's an example of a simply supported floor panel with a UDL applied. The bending the shear checks carried out using the appropriate clauses of AS 1720 Part 1. They're sort of listed on the slide there. So note that in both these cases, it's because these are strength checks, we're looking at the effective section properties in the calculation. It's probably a little bit hard to see there on some of those diagrams, but the same K factors are applied, and the material strength factor is equivalent to that that's used for glulam in those shear and bending calculations. So looking at there, we've got, if you're looking at, say, for a glulam beam, for example, there's only one flexural shear check to take into account, but the CLT is a little bit unique in that you're looking at rolling shear as well as direct longitudinal shear of the boards. So I won't go into too much detail there, but it's usually the rolling shear failure that kicks in first, just because the rolling shear strength is quite a lot lower than the longitudinal strength of the board. But in either case, when you're looking at a simply supported floor like this, it's normally deflection that kicks in the limit of deflection will kick in well before you get close to the failing the panels in shear. And then again, bending failure below. You're using the same K factors and the effective section modulus for the bending failure. And you can just see a couple of photos there showing an example of the different types of failures. So the rolling shear failure has got that characteristic curved failure mode as the transverse layers fail in shear and the material rolls over itself. So just another example where 1720 does apply in floor serviceability. So that this is a deflection for a simply supported panel. So we're looking at, in this case, the apparent stiffness. So as I mentioned before, the effective stiffness is looking at strength, and the apparent stiffness is what you're looking at for deflections. So there's a published table setting out all the apparent values of stiffness. And I guess a key point to note, which is a little bit unique for the design of CLT, is that the apparent stiffness value varies with span. So you've got to calculate the correct apparent stiffness with the span, and then that feeds into your deflections. And as the span increases, the apparent stiffness tends towards the effective stiffness as the effective shear deformation becomes less. And the other aspect of 1720 that's being applied in that is that the J2 factor of 2 is being applied directly to get the long-term deflections of the CLT. I guess an interesting point to note is when you're using European codes designed for, say, European CLT, sometimes that factor of 2 is, it comes down to 1.6 under the European standards. And it's an area, I guess, it's hasn't been heavily researched whether J2 is the appropriate long-term factor to use, and then potentially maybe some conservatism in there, but that's the number which we're recommending to use at this point of time. Okay, so moving on to an example of wall design. So walls can also be designed within the 1720 deemed to satisfy pathway. So again, we've got the section properties that we've determined previously, and when we're looking at walls, we're looking at that typical sort of 1 meter long run of wall and working out the capacity of a wall the same way that you would for a concrete wall or an AFS wall or something like that. So working out your effective section properties per the meter length, apply the same K factors, material strength factors, and you're looking at the slenderness coefficients in the same way that you would for other timber products within 1720. I guess some of the key things to consider for walls, the capacities can be quite impressive, and then for the axial capacities, but you really need to look at eccentricity as well, because that basically gives you your bending moment, and that is compliant. The bending is applied simultaneously with the axial loading to get your overall utilization. So the eccentricity moments can be significant, particularly in the 3-layer panels. And those eccentricities can come from how the load's applied, or even you can see on the right-hand side a figure of a charred representation of a charred panel where as the charring continues, the eccentricity between the load application and the neutral axis shifts. So there, when you're looking at walls, that's an aspect that you don't want to neglect. Again, so that pathway can apply, and that's a 1720 calculation that feeds into a DTS. So moving on to aspects of CLT design which aren't covered under the DTS pathway, floor crushing is, when you're looking at mid-rise CLT buildings, floor crushing is one of those applications that does start limiting the height of CLT buildings depending on how you're looking to construct it. And AS 1720 is not intended to cover this aspect of design, and it's really the best references that we believe are available for this are what's covered in Eurocode and the ProHoltz recommendations and guidelines for that. And I guess the other things we'd recommend around that is when you're looking at the perpendicular to grain strength of CLT, be careful of what values you use. We provide guidance in our structural design guides, but people can use values which are higher than what's intended based on feedstock properties, and you really need to use properties that are appropriate to the overall panel to make sure that you're not getting excessive deformation or shortening. So crushing is a limit state. It's a material failure, but you also want to look at the elastic shortening between the floors as well. And if that becomes a limiting factor, there are options to reinforce the floor to bump that up again. But so again, you've got to come up with a rational pathway, have a method, and publish that under the proposed performance solution. Another aspect where 1720 doesn't apply is looking at punching shear. So rolling shear and punching shear are definitely related aspects of the related failure modes. So they're both failures that result from failure of the transverse layers. So rolling shear is generally associated with a line support, whereas punching shear is basically a point support. So this can come from heavy point loads like a column or a heavy wheel load, or it could be a point support at a column interface, or maybe a post and plate floor. So I guess particularly in reference to the post and plate systems, as there's growing interest in the post and plate systems, there's more and more testing and destructive testing that's been done to look at these types of failures. Sometimes you can treat it as a simple one-way shear system and conservatively ignore the second direction case, but that becomes more challenging when you're talking about edge conditions and corners. And in some cases, if you've got particularly heavy loads that you can't look to assess by more simpler means, you may need to do some project-specific testing for that. So just, I guess, anecdotally on most of the projects that I've been involved in, I've worked on a post and plate project, designed one of those, but the punching shear hasn't normally been an issue on projects, and most of the cases when we have had significant point loads, it's been able to be dealt with in a simplified sort of one-way shear check. So one of the key areas where I think where particular care does need to be made around areas that aren't within CLT are the in-plane actions. So CLT are mostly used in floor and wall applications. They can also be efficient in resisting loads as beams or lintel members that are loaded on their edge. And in-plane bending also occurs in CLT floor diaphragms, CLT walls and lintels, and also in stair stringers you might see on some projects. So one of the advantages that CLT can offer to that application is the tensile strength perpendicular to the beam length that's provided by the orthogonal layers that makes the CLT beams less likely to crack parallel to the grain. So as a result of this, it can be quite handy for incorporating penetrations. So the top two figures show two different 3-layer beams under in-plane bending. The beam on the left has the outer layers parallel to the beam length, which is generally the favourable condition that you'd like to aim for. while the one on the right has its outer layers vertical, and that could be considered to be a wall mode, or say if you had a wall panel and you've cut out a large opening, that's the type of section that could be remaining above the door. So the same could be considered for 5 and 7 layer panels. So while there's been a significant amount of research that's been looked at for the panels under out-of-plane bending, and the design approach values and strengths are well understood and agreed, for CLT under in-plane loading, there's been comparatively few studies that have been done, and the accepted and the detailed methods and having sort of simplified methods, I'd probably say, are still under development. So besides, when you're looking at in-plane bending, that you've got to look at 3 things. One is a bending mode, and then there's 3 different shear checks that need to be taken into consideration, which I'll show on the following slide. So the photos on this slide also show a couple of applications on real projects where this has come up. So the first one on the bottom left is a house where the side walls are acting like a cantilevered deep beam. And then there's a folded plate roof where there's aspects of the behaviour to an in-plane bending. And then the one on the bottom right, it's not a great photo, but it's a header beam, large opening over a garage door where that CLT panel is acting as a beam. So looking at the in-plane shear in a bit more detail, the first thing we need to consider is the in-plane bending capacity. So similar to the out-of-plane bending capacity, you're looking at how much fibre, or what's the effective section that's acting in that plane. So one of the things that you need to be careful about with that is what's the orientation of the fibres in the right direction. Like when you've got the outer layers running horizontal, you've got more effective fibre in that direction compared to when the outer layers are running vertically. But you also need to be careful that you're not treating it as a glulam beam, because it varies between manufacturer to manufacturer, but XLAM doesn't glue its edge boards. So you need to be careful that you're not making the assumption that this is acting directly like a glulam beam. And also, I mentioned earlier that XLAM features lower grade material on the inside of the panel. So that can actually, it needs to be considered in the residual strength, and that you're not assuming that you've got higher strength material that's resisting those failure modes than you might otherwise have. Looking at the shear failure modes, shear failure mode 1 is characterized by a shear failure which is parallel to the grain in the cross-section of the beam. And failure mode 2 is characterized by a shear failure perpendicular to the grain in the net cross-section of the beam. So they're quite difficult to get your head around, those failure modes, and through the description I've just given, but probably the easy one to sort of visualize is failure mode 3, which tends to be the lower capacity of the 3. I mean, it's obviously recommended to check all 3, but the limiting one tends to be of the 3 shear failure modes, and the overall limiting one tends to be the bending one. But of the 3 shear failure modes, it's the twist off failure of mode 3. So you can see on the diagram the little spirals, which basically the calculation method is to look at what's the shear stress on those little overlaps between the panels, between the lamellas, and then compare that to a torsional strength of the adhesive. So I guess the point is that none of these methods are included within AS 1720, so you have to come up with a rational basis for documenting that, and in some cases that might need to be supplemented by testing again. So to that point, XLAM have been looking at doing a range of in-house testing to better understand the in-plane strength and stiffness of the panels. So there's all those modes I showed in the previous slide. They're all to do with strength, but if you want to use that as a beam, you also want to know how stiff these things are. So we looked at doing a couple of quite a few. I think it was about 5 sets of 15. Short and long beams, 3 and 5 layers, lamellas in different orientations, and we've got some really interesting results. And we found that the bending failures, that's sort of a bending tension failure of the bottom lamellas, were almost always limiting the capacity of these lintels or beams. Even when you were down at very short spans, when you were trying to force the shear failure, we're still getting a bending failure at those middle lamellas. So the published guidelines aren't providing this method to have the in-plane stiffness at the moment, but we're collating all this data, and we're hoping to publish that in the not too distant future. So moving back briefly, just to look at some aspects of the fire design and compliance. One of the areas that is covered under the existing Australian DTS pathway is the process for looking at reduction in section of elements by looking at char depths using the methods in AS 1720 Part 4. So that standard allows the char rate of products to be determined on the basis of testing that's carried out in accordance with 1530 Part 4. And the typical elements that you'd be looking to check for this in the context of mass timber buildings is beams and columns, and that's an aspect that is covered in those standards and technically is covered under that DTS pathway. So extending the concept of beams and columns, glulam beams and columns to CLT walls. When you're looking at things like CLT apartments, you can sometimes have a number of walls which are fully within the apartment. Sort of an analogy might be a blade wall in a concrete building, where you've got a CLT wall that's fully within a fire compartment, so it's exposed to fire on all sides. So what XLAM have done is we've basically we've looked at a whole range of fire tests that we had for different elements. We looked at the char rates, and we basically determined an appropriate char depth for a blade wall that's exposed to fire on all sides. And then we've published this data on char depth, and that allows designers to determine the residual cross-section and then look at the capacity of this wall acting as a blade wall. And we think this is going to have some good applications for apartment buildings. So that's information that can be taken, and because it's not part of a compartment boundary, all you need to look at is the structural adequacy in doing that. And so here's just an example of the table from that shows the residual sections. So after different periods of fire exposure, with either no plasterboard encapsulation, one layer or two layers of encapsulation. And the analogy of, I guess, the glulam beam is the CLT band beam. So that's when you've got CLT acting as a wide, shallow beam. I won't go into the applications of that and why that is, but it's a way of doing certain types of CLT floor systems, and then using that same assessment and the effective char depths, the designer can again determine the residual cross section, use that to determine the bending shear and punching shear capacities, and then use that to look at the structural adequacy of that at a different period of time. So I guess probably worth just pointing out that when architects and different designers want to use that system, there's often a desire to expose the band beam or expose as much of the timber as possible. But when you're looking at these char depths at certain spans and fire resistance levels, it's the char of that system that is going to limit how much of that can be exposed and when encapsulation is going to be needed. So again, that's just similar to the previous table where it shows for different periods of fire exposure, whether you want to expose the band beam, have one layer of encapsulation or two, how much char has occurred, and then you feed that into your residual section calculations. So just to finish off, just to throw in a bit of a change of gear to what we've just been, the deep dive into compliance and DTS and things like that, just to throw in a couple of my, rules of thumb that I think come into a lot of projects. I guess the first one is, time is in the detail, money is in the detail, and devil is in the detail. There's a lot of things which affect the aspect of CLT projects, and it's bringing as much experience and getting as many of things right is critical for getting these projects going ahead. Another rule of thumb is that if it's difficult to draw, it's going to be difficult to manufacture, transport, and assemble. So keeping it simple. Every time you relook at an aspect of design, maybe think how can we make this simpler? That tends to pay dividends. And also the idea of evolution, not revolution. So when we're looking at similar projects over time, keep as much of the keep as much of the design or connection details as possible to what worked well previously. Look at the things that didn't work and maybe try and change 10% of it each time, and slowly will get better over time. And if you're getting 10% better on each job, sooner or later you're making great steps. So thank you.
Thank you, Tom, for your input today. Well, now it's our audience's turn to get involved. A big thank you to everyone who submitted your questions via the chat box today. We've had quite a few come through, so let's kick off. Now, my first question, I'll direct this one to Fiona. So Fiona, questions come through from Mario from New South Wales, and it is mass timber structures use softwood. So how do you prevent termite attack?
Oops, sorry.
All good.
Can you hear me?
Yes.
Sorry, can you hear me? Okay,
Yes.
cool. So firstly, we need to provide a physical gap, the physical barrier, such as provide the gap and use a concrete slab instead of have the timber touch the ground directly. And also we can provide an H3, which is the level 3 treatment to the timber to prevent from the termite attack.
Thanks, Fiona. Tom, I've got a question for you, and Steve Hubbard was very early with submitting his question today, and it was he's interested in designing mass timber structures that are exposed or partially exposed to the elements. If you could provide some advice on either suitable weather protection coatings or timbers.
Sure. I guess probably really sort of generally that would depend whether you're talking mainly about glulam or CLT structures. But I guess glulam, anything which is exposed, you'd be typically looking at either a product with a natural durability timber or a treated product with a suitable coating system that gets maintained sort of periodically from time to time. And I guess CLT is primarily intended as a fully protected product, so you're not usually looking at doing external structures with CLT. You could potentially do external soffit areas that are fully covered by overhangs of the building, but not direct weather exposed CLT.
Thank you. Well, Tom, I probably have another question for you, and it's with regards, and a couple have come through from Dilip and Tom, questions around the mass timber structure and how it behaves in earthquake-prone areas. So I suppose the first one was, has it been tested against seismic loads to assess its behaviour? And then around, are there inelastic design methods for design of MTC for seismic?
Sure. Yeah, definitely. There's a lot of research around the world looking at mass timber, and I guess maybe just to hone in a little bit on CLT in that question. There's definitely been research, and in general, the sort of findings are as mass timber structures perform quite well in seismic applications. I guess what the challenge where we're sort of seeing, I guess, with the existing sort of the traditional timber design codes, they're not, at least in Australia and New Zealand, they're not geared towards mass timber construction and detailing yet. So I guess the challenge is it comes down to how you connect the panels together. The panels themselves are very strong and robust, but it's the joints that you're looking at. What sort of ductility can you get out of the connections, and just how you sort of conduct that within the framework of the codes. But in general, it performs very well seismically.
Tom, just quickly on that, you kind of referenced the Australian standards. A question came through from Assad Ali when he registered, and it was really, the question was around what Australian standards are applied to mass timber construction, which I think that Fiona and yourself have commented on. And then it was, can we see a separate standard for mass timber in the near future?
Sure. Yeah, I guess the part that I was touched on in my part of the presentation was looking at all those currently existing Australian standards, and I guess material feedstock testing standards, that type of standard which currently exists for traditional timber construction. And then things like the AS 1328 standard for glulam, which is currently referenced under 1720. I guess my personal feeling is that at some point, the CLT might be integrated in a similar way to how glulam is that it's referenced as one of those, referenced materials, and there's essentially a manufacturing standard and material property standard that sort of gets directly referenced in 1720. But as to when, I'm not 100% sure when that will be at this point in time.
Now, Fiona, there was quite a few questions, quite a bit of interest with regards to the grade 4.6 bolts for timber connections. Michael had the question, what is the reasoning behind the use of the 4.6 grade bolt?
So actually, it's a requirement from 1720 Part 1. It's a clause called 4.4.2.5, which has a requirement for maximum tensile load capacity for the bolt. For 4.6 bolt is 400 MPa tensile strength compared to 800 MPa tensile strength for 8.8 bolt. So besides the requirement from the Austrian standard, also we would like to see it's better to have the ductile deformation in the connection instead of having the material failure. So that's I think that's another reason why we use 4.6 bolt instead of 8.8 bolt.
Thank you. Now, I've got a question which has come through from Rafe, and the question probably for you, Tom. Does DFMA offer the opportunity to fabricate CLT or glulam beams with a pre-camber to address long-term creep deflection, or is the reduction of beam size also limited by vibration issues?
Yeah, definitely. No, I guess the first part of it, the opportunity to fabricate, not CLT, or at least speaking from XLAM's perspective, first of all, XLAM can't pre-camber CLT. Glulam beams can be pre-cambered, and again, from our perspective, there are some limitations on then what you can do downstream in terms of CNC work on a pre-cambered beam. But yeah, we definitely can pre-camber beams, and our standard glulam range does have a pre-camber essentially set into it as a radius 600 meter pre-camber as standard. And then different manufacturers will have different limitations around that. But yeah, I think for floor beams, for roof beams, the pre-camber can definitely have an advantage when you don't have that vibration criteria. But I have seen on some jobs where there wasn't an advantage to pre-cambering floor beams because the vibration limit was tapping in basically, and it's not giving an advantage in that sense. And I think, I guess, from more broadly on DFMA, when you're getting towards talking about site installation and keeping things nice and simple on site, in my opinion, I guess at least I think having straight beams can be easier when you're trying to it's just one less thing to worry about getting right when the beams are treated as straight, and then the tolerance around that rather than having the added complication of how much it will sag under a pre-camber situation.
Excellent. Tom, I'll keep it with you. We had a question come through for Cornell engineers. And if a CLT floor panel or column is damaged during a fire or by moisture degradation, what is the standard procedure for repairing the damaged panel or column?
Sure. It's, I guess the first thing to look at would be just, I guess, accurately assessing the extent of where it has, where the damage has occurred. And if you're talking about long runs of wall, if the fire has occurred in that whole room, and you're basically, so the lamella the outer lamella or significant part of that whole wall structure has been taken off over a large length of wall, then the repair process definitely becomes more challenging, and that would, I guess, apply to a floor as well. If you've got a more localized failure, say around a bit of, say, some damage or a local bit of decay on a wall panel, it is possible to remove a short length, just remove the outer lamellas, sort of route out the damaged areas, and you're normally going back to when you get back to the next full lamella, and then so you say if it's just the damage on the outer lamella, so you take off, get rid of that full depth of the outer lamella, limit the extent along the length of the wall as much as you can, plane it back, and get the surface finish back to a level where you're confident that the repair adhesive that you're using is going to bond that adhesive, and then you're normally looking at a combination of glues and screws to get that replacement lamella back in place. I wouldn't say it's a fully standard procedure yet, because it's a lot of it is case by case, and you've got to consider what else is happening in the structure, whether it's how heavily loaded certain parts of the structure are, or what extent it might be happening on. But normally, if you can limit it to, say, less than 10% of the length of the run, you've normally got a pretty good chance of getting away with that repair process.
Thanks for that. Now, Fiona, I've got another question about the grade 4.6 bolts, and this one's come through from Donald Robertson. So a big hello to Donald, who's watching live. He just asked the question, what is the reason for using grade 4.6 bolts as opposed to the grade 8.8?
I think similar to what I just answered before. So it's more about the ductility. Besides the requirement from the Australian standard, it's just with higher tensile strengths, it's not gonna yield like before it hit with the force. But with a 400 MPa bolt for the 4.6 bolt, it will yield earlier. So it's safer to see the ductile deformation at the connection just before the timber, like brittle failure in the timber.
Thank you. Nicole Brown has asked a question. So hi, Nicole. And I'd say that this one would be for you, Tom. So what treatments are required for glulam beams applied within aquatic environments?
So I guess for in terms of aquatic environment, assuming that's sort of referring to a swimming pool or something like that. We would generally recommend using sort of an H3 treated glulam in a swimming pool environment, and then with an appropriate sort of coating system to go with it. And I guess the other thing to be looking at is just making sure that the environment that glulam beam is in, that you've got a reasonable feel for what the long-term moisture condition that beam's going to be exposed to, so making sure it's not remaining elevated over long periods of time, and there's sort of adequate ventilation. But so generally an H3 treated glulam, or a high natural durability product.
Thank you, Tom. I'll just kind of keep it with you. Another question for you. So sorry about that, but you're on a roll. This one's come through from Nathan, and he has just asked if you could comment, and maybe both of you may want to jump in on this one, to please comment on carbon emission comparisons of steel concrete versus timber structures.
Sure. I guess the embodied carbon aspects of the product is definitely not my number one area of expertise, but Excellent does have a detailed EPD for the product, and that covers sort of the full. It's the everything related to the production and supply of that product. So it covers all stages of forestry, transport, manufacturing, end of life assumptions, and that's all covered under the that EPD. So that's available. So the people that are carrying out those assessments on projects, they have access to that information and can plug that into their models in order to make those comparisons. But I guess Generally, we see that using mass timber on building projects is seen as a pathway to getting a reduced embodied carbon on a project.
Thank you. Fiona, did you want to add to that?
So it's similar to Tom. It's not my area of expertise, but with timber itself, the material is just when you cut the timber off, the carbon will just install in the timber. So that's why when you see some comparison, you'll see why timber is negative in carbon emission instead of positive. But the concrete is still different. Is will have the carbon emission during the lifetime. But we do need to consider the whole process from the forest and manufacturing and even transport and packaging. As Tom mentioned, it's all in our EPD. We have the assessment for as of an example. So yeah, if people keen to see it, and it probably is a very good document for people to have a look.
Excellent. Fiona, a question for you, which has come through from Val Vishwanath. What kind of connections are used between the members of glulam trusses? Is it still steel plates?
Yep. So I think it really depends on the span and the force. Normally, when you use glulam, it is like a high span, the truss. So with the high force, we normally use a steel plate and the bolt for the connection. But when it's come to like a small span, we probably even won't use glulam because glulam has very high strength. We probably use like LVL or like a lower strength timber if it's not exposed.
Thank you. And Tom, I know we're coming up to the end, but I've got a couple of questions to go. One is, what is the recommended fire protection material for timber beam?
Yeah, so I guess if you're looking to add an enhanced fire protection to a timber beam, so I guess speaking about glulam specifically, if you don't, you can expose the glulam directly and look at designing that beam with the required amount of char depth to that glulam beam. And if you want to enhance that, you can look at putting standard would be to use something like a fire rated board. Standard would be sort of 16 millimeter fire rated plaster board. But there's other sort of manufacturers that do equivalent products to basically give you a layer of encapsulation around that beam before you start charring the timber itself.
Thanks, Tom. Look, I think we are coming up to the end of our Q&A, but we had a really good question come through, which I thought would be perfect to end today's session. So big thank you to everyone who has submitted, and apologies for those questions that we have missed. But the questions come through from LG, and they have asked, having gone through the learning process yourselves, how would you suggest structural engineers take on the introduction into CLT? I thought that would be a good place to end today's session. So any advice for the structural engineers out there?
Do you want to take this one first, Fiona?
Yeah, probably it's a good question for me, since I just have like 1 year experience now for the CLT design. So Australian standard is covering some of the timber, but the CLT itself, it wasn't covered in that standard. But there's plenty of material, such as the one we have presenting or the beginning of the presentation. The FP innovation is very good. That one is very comprehensive guidance and handbook for designer new to the CLT. And also we have the wood solutions and woodworks. They have a lot of good material and video for people to learn from. And also there's a portholes And for our XLAM, we have a lot of like guidance and materials such as like calculation samples. For engineer can see how we can calculate the floor, which floor thickness we should select based on the floors, and with a point load as well. If it's a UDL, we have our span table for people to use with different SDL and left load to select from for the floor and the walls. And like one of our colleague, and she's taking the master course in UTS, and they have the timber engineering course, which is very good for the student if they want to learn like in the like system learning. I think they are teaching some CLT as well. So that's probably my personal experience. And also for the program, we normally use this RFEM. It's a double part of the double program. It's not that difficult to start. Like if you know the program, such as like a ETABS or robot, it's a final element software. So it's just for both of beginners and like someone has background of structural engineering and has some knowledge. I think it's just to wait for some advice for them.
Thanks, Fiona and Tom.
No, it's a really good question. Yeah, and I think it's it's definitely something I found challenging when I first jumped into mass timber, because it was very new at that point in time. And I think probably the biggest difference for me was just really fortunate to be in an environment where there was space to learn on the job, and have sort of the right people supporting that learning process, and having the right projects. So I guess if anyone that's sort of leading design teams, or mentoring more junior engineers, the opportunity to create that space where people can learn on the job is, I know it's not easy, but it's made a huge difference for me. I think second the points Fiona said about the Wood Solutions information. It's a really great resource, and I think just also looking to what's happening in other markets, in like European market and North American market, and just seeing how they're doing things, and learning from them as well.
Excellent, great advice from the two of you. Well, look, that's all the time that we have for today. So please join me in once again thanking our speakers, Fiona Zhang and Tom Watts, for their time and input. I would also like to thank Engineers Australia's industry partner, XLAM, for their support with today's webinar. On another note, I'm very excited to announce that Engineers Australia's 2024 Climate Smart Engineering Conference, the early bird registrations have just been launched. So please follow the QR code on the screen for more information. And then also, if I could ask everyone to please complete the short feedback form, which is linked in the description box below. It really does help us to improve and plan our future sessions. So finally, thank you again for joining us with our webinar today, and we hope to see you at our next Thought Leaders event. Good afternoon.